For the purpose of the navigational aid for the blind, we have worked with two operating systems, the Angstrom and the NAT 11.04. Firstly, the Angstrom. The video shows the booting of Angstrom and all the loading of its drivers. The login screen appears as soon as the drivers are loaded. Here we enter our username and password. This is the Angstrom environment, the graphical user interface. And this is the terminal where we input our code and where we run the image processing algorithm. This is the NAT 11.04, which is a Linux operating system. The video here shows the loading of several of its system services and drivers. We chose to work on NAT 11.04 to compare to Angstrom because of one main reason, which is the availability of webcam drivers. This is the login terminal where you enter your username and password. The GUI of NAT 11.04 is quite similar to Angstrom. This is the working environment of NAT 11.04. This is the terminal where we enter our code and where we run on the image processing algorithm. We are using a Logitech C100 webcam, which is a very inexpensive webcam. It is a UVC or a plug-and-play type webcam with no special drivers that have to be installed except the UVC driver. The webcam is installed on the board and it is the eye to the entire system. It is attached to the BeagleBoard via USB, which continuously renders color frames to the BeagleBoard for image processing. The frame size rendered is 640 by 480. We have experimented on several other webcams such as Logitech C200, Sony and Zebronics. The BeagleBoard is an ultra low cost, high performance, low power OMAP 3 based platform from Texas Instruments. It is the central processing unit of the entire system. This unit analyzes the images received from the webcam and detects obstacles in them. The board also receives signals from a sonar module. Based on the input from the webcam and the input from the sonar module, the board outputs several control signals which are sent to the motor driver module and the vibrators. The two white ICs on the breadboard are the optocouplers and the black IC is the motor driver L293D. The optocoupler provides ohmic isolation to the BeagleBoard. The maximum voltage output at the BeagleBoard GPIO pins is 1.8 volts. This voltage is not sufficient to drive the motors of the system. The optocoupler receives power from an external 6 volt supply and hence the 1.8 volt signal of the GPIO is converted into a 6 volt signal by the optocoupler. The output of the optocoupler is connected to the motor driver, which is the L293D chip, which provides sufficient current amplification to run the two motors. The BeagleBoard produces a PWM which is fed to the board through the optocoupler and the motor driver. The duty cycle of the PWM is varied to change the speed and the degree of rotation of the motors depending on the nearness of the obstacle from the camera. The oscilloscope shows the output of the PWM. We are using the demultiplexer AC139M from Texas Instruments. The demultiplexer output pins are connected to two vibrators, one on the left side and one on the right side of the belt which the user wears. The BeagleBoard GPIOs provide two inputs to the demux for choosing whether to go forward, left or right. Using sonar to detect walls perpendicular to the camera, sonar transmitter transmits a square wave of 40 kHz as carrier which is produced by the TNC 555 timer from Texas Instruments. Sonar receiver produces a sine wave output if the carrier is received. The oscilloscope shows the output sine wave when the sonars are directed towards each other. Once the sonars are directed in different directions, the output at the receiver becomes 0 as shown in the oscilloscope. The output sine wave is converted into a 1.8 volt DC signal using an RC circuit and is 0 when the sonars are not directed. This is the setup of the obstacle and the board. The right half is the original image and the left half is the segmented output. The right half is the thresholded output and the left half is the contour. The right half is the contour and the left half is the bounding rectangle. The same algorithm has been performed on a different test case. This is the demo of the implemented algorithm. The first two test cases are for single obstacles. The later test cases are for multiple obstacles. We are showing the demo on a board because it is more explanatory as compared to showing a man. Obstacle avoidance can be clearly seen from the motion of the board. The same principle is also applied to the motion of a man.